Hello, everyone. My name is Dr. Destenie Nock, and today I am going to talk to you about how my team and I have been thinking about incorporating the ecological impacts of wind energy deployment into renewable energy system analyses. So, this is a paper that has recently been published by my co-authors and I. This is a collaboration between the Massachusetts Institute of Technology, Carnegie Mellon University, and the University of Massachusetts Amherst. I'd like to thank Olivia Pfeiffer and Dr. Aaron Baker for helping with this work. So, we have been focusing on the New England region, and that's because many states, Massachusetts and Vermont included, joined the US Paris Climate Alliance to honor the Paris Climate Change Agreement. In this region, there are many talks about retiring power plants. For example, between 2012 and 2020, 4.2 gigawatts of generation capacity was slated to be retired. In addition, there's 5.5 gigawatts of coal and oil capacity that are at risk of retirement. And there's also uncertainty surrounding the region's remaining 3.3 gigawatts of nuclear. So we know that there's going to be a lot of changes, and offshore wind has been proposed as one of the technologies that could aid in this energy transition. To date, most of the studies that have been investigating the different sustainability of energy technologies has focused on individual technologies. Maxim 2013 compared 14 individual technologies across 10 sustainability indicators in a global context, while Klein and Whaley 2015 compared 13 electricity options across 8 different decision maker preference scenarios for the United States. But one big differentiator in our work is that we consider the sustainability of the entire system rather than one technology at a time, because we know that the sustainability of the whole system is not necessarily equal to the sustainability of the parts of that system. And also, only investigating the direct energy impacts of a technology will not highlight how the interactions between technologies will affect our larger sustainability objectives. So let's first talk about some of those direct impacts that offshore wind energy might have on fish populations and sea life. So first, there could be acoustic disturbances. Often we think of this happening during drilling, where you're really pounding into that sea floor. Electromagnetic fields could be created around the electric cables, taking that energy back to land. There are some benefits like habitat gain that we could have for juvenile fish, but there's also a risk of like fishery exclusion. Some people are worried about tourism. And so these are like direct impacts from offshore wind energy deployment. But what about the indirect impacts, which result from a changing energy system? So let's talk briefly about that. So first, we have some offshore wind, right, being deployed in the New England region, and spikes and falls in wind energy may be balanced by hydropower. Now, these spikes in hydropower generation could impact river flows, which then we suspect would impact fish migration. So just to make sure we're all on the same page, when I talk about hydro here, I am talking about a traditional hydropower plant, which is a run-of-the-river hydro plant, where we have the river at the top. This would be taken into a penstock, which is a nice little tunnel that then lets the water flow down into a turbine and generator power station. Water flows around that turbine, generating electricity, which then sends it to the grid, and then it feeds out in step 5 to the lower river. So when I say hydropower plant, that is the type of hydropower facility I am referring to. New England has multiple hydropower plants along the Connecticut River. And as you can see here in this map, the circles represent those traditional hydropower plants, and the triangle is going to represent the region's pumped hydro storage facility. Now, the challenge here is that dams can seriously impede fish migration and presents multiple change points for river flows. And so here we see that along this entire river, we have a good number of dams. But how does this impact fish, right? So it can impact them during their reproduction and early life cycle stages, where fish are highly sensitive to variability in river flow. If we have a very high amount of power generation coming from these hydropower plants, a fast river flow can create challenges for juvenile or weak fish in terms of their migration. But if there's really low generation, then this can create a reduced flow or a lake effect. This can be very confusing to the fish because they are expecting a current to tell them which way is upstream, right? And so that they know which way to migrate to. And some studies have found that fish avoid migrating during changing flow magnitudes. And so to minimize the ecological impact, it is recommended that discharge is stabilized during the spawning periods. And this is going to mean that there could be additional regulations on hydropower operation as we're moving to that 100% renewable energy future. And so we're going to need to take this into account as we are thinking about what technologies we're going to be using to balance the grid. So what months could, this fish migration impact the way that we are managing the grid? So this is a table of the different fish species that are of concern within the Connecticut River. There are 9 fish species. Along the top row, we have the months of the year, and along the bottom row, we have the total fish species of concern. So if we were really, if we're really worried about fish migration periods, we want to look at those high migration times. And here we see that May and June and July are going to be those highest months where we see a lot of fish migration activity from multiple species. Now, there's also the concern of where exactly is this happening? And so this map here is showing you the number of fish species under concern. We see a lot of fish species at the bottom, kind of towards the ocean opening for this river. And that is because of those dams impeding that fish migration for these kind of upper levels of the Connecticut River. And we see the other map here is the blue and green one, is showing you the number of fish species with high spawning seasonality. And so the darker the color on these maps, the more fish we would say are of concern at these different points along the river. In our methodology, we combine an electricity model with an ecological impact analysis. So the way that the electricity model analysis is going to work is that first we take in hourly demand, renewable energy resources, nuclear outages, and other power plant restrictions. We input some initial generation capacity levels. We are saying that this might be the level of generation we see on the power system at this time from these different power plants. We run this through an electricity model, which is going to check to make sure it's reliable. And here we are defining a reliable power plant mix as one that can supply energy at all hours of the day for all years within the study. If we say that if the model deems the power plant mix is not reliable, then we report that we need to add more capacity and we would need to rerun the electricity model until it becomes reliable. Once it is deemed reliable, we're going to output that energy by source. Then we're going to calculate the changes in hydropower generation. We then calculate the estimated changes in river flow. And this allows us to investigate how river flow changes correlate with migration periods and the different fish species of concern. So our key model assumptions for the energy model are that this is a resource adequacy problem, meaning that our key goal here is to ensure that there's enough generation capacity to satisfy demand. And this generation capacity that we allow in the model is going to be a mixture of hydro plants, natural gas plants, nuclear power plants, solar farms, wind farms, and oil plants. And I would definitely encourage you to read Nock and Baker 2019 if you would like more information about our electricity model. That is where the original model documentation has been published. So measuring hydropower variability, this is going to be a function of the hydro generation at time t+1 subtracted from hydro generation at time t. So really we're concerned about the differences between hour 1 and hour 2, because that is what's going to cause those spikes and dips in the flow variability of the river. This is one output from our model. So in this graph, on the x-axis, we have the hours of the year. Along the y-axis, we have the generation from hydropower in megawatt hours. And this is for the low wind case, which means that the New England region is going to deploy 1,600 megawatts of offshore wind capacity. So here, the black line represents the 50th percentile, and the red lines, the red dotted lines, represent the 90th and 10th percentile of that ramping period. And one thing that we notice is that only 7% of our hours of our study see ramping periods where we have more than 2 megawatts. But as we increase, so now the second graph that has appeared shows the high wind scenario, or 10,000 megawatts. We see that there are much larger periods of ramping, and 19% of our hours now have a ramp greater than 2 megawatt hours. One thing I do want to note here is that New England is a natural gas dominated system, which has been reflected in the electricity model that we use. So as we are moving to a fully renewable system and retiring those natural gas plants, we would actually expect to see these ramping periods increase significantly. So over the course of this analysis, we were increasing the offshore wind capacity in stages between 1,600 megawatts and 10,000 megawatts of offshore wind capacity deployed in the New England region. And here we see that there is a widening of the daily peaks and daily lows as we are increasing that offshore wind capacity. Specifically, the daily low is going to, can dip down. And one cause for that might be that there is enough offshore wind capacity in those high deployment scenarios that would, lead to not needing to source as much energy from hydropower and natural gas. So as offshore wind is displacing hydro, then we might actually find that we're seeing some of that lake effect, which can occur from low generation periods. And if this is happening during those high migration periods, this could be a cause for concern because the fish would be expecting a current and it can confuse them. So let's talk a little bit about, when we actually see those ramping periods and how that corresponds with migratory fish. So on the x-axis, we have the different months of the year. On the y-axis, we have the number of active fish species. So the number, and that's the y-axis on the left side, the number of active fish species is going to correspond to those gray bars. Then on the right-hand side, y-axis, we have the absolute hydropower ramp in megawatts. So that's the change in energy power output from hour 1 to hour 2. And the blue lines represent the high offshore wind deployment scenario, and the red lines represent the low offshore wind deployment scenario. One of the big things that we notice is that there is a high level of ramping occurring in January through April, but that actually is some of the months that correspond to those low migration periods. So that is, one potential upside of this. Now, as we're moving into May, June, and July, we do see that the 90th percentile of those ramping periods in the high and low offshore wind scenario, they're pretty high. So that would mean that, system operators and hydropower operators would need to think about the ecological impacts of primarily using hydropower to balance offshore wind and what impact that might have, and how the regulations on river flows may impede their ability to fully balance out offshore wind energy. And so this would also, lead us to want to consider other technologies like storage, demand response, and make sure that those are in place to help accommodate these challenges. So here we are going to talk a little bit about how we measure the river flow impacts. And this is our key equation. So P is the average hourly hydropower output in megawatts. That's going to be equal to the density of water multiplied by gravity times the maximum dam height above the river multiplied by the mass flow rate of water through the generators in cubic feet per second. So this is going to be the main equation that we are going to use to estimate the river flow changes and we're going to be solving for that Q. So the river flow changes. The hydropower ramp of 4 megawatts was what we saw in our 90th percentile in our high wind case. And we saw that this led to an increased river flow by 800 cubic feet per second. Now we approximate that this would lead to a change in river elevation of about 0.026 feet per hour. And this is based on specifications from the Wilder Dam in the Connecticut region. Now, while this elevation change is safely within the bounds of the operating limits, we do note that a large portion of wind variability, again, in our model was absorbed by natural gas, and a lot more wind will be deployed in a 100% renewable energy system, and there will be less natural gas, of course, in a 100% renewable energy system. So as we are moving forward, we need to think about what technologies will need to be deployed to help balance out the system. As I said, that could be demand response, other types of storage, as well as hydropower. So in conclusion, our results indicate that an increase in offshore wind capacity will lead to larger ramps on the river. This may adversely affect and impact fish, especially during spawning times. One of the things we find is that the average ramp of hydropower increases linearly with the capacity of offshore wind, and the minimum level is often reduced. So, if you leave with nothing else from this brief talk, it is one of the main things that we have found is that we need to really think about the system and the implications of a changing energy system and how those technologies interact with each other, because there will be trade-offs as we are moving to a fully renewable system. So I would like to thank all of you all for listening to my talk today. And this paper has been published in Renewable and Sustainable Energy Reviews. And I encourage you all to look there for more details about our analysis.